Good morning, everyone. Today we are going to perform an experiment to calculate misalignment losses at the fiber joint. In this experiment, we will simulate, calculate, and plot the lateral and angular misalignment losses at the fiber joint in LABVIEW. This will help us to understand the misalignment loss at a fiber joint in optical fiber and its impact on the output. And we will also be able to analyze and observe the variation in the loss with the changes in the misalignment, that is angular and lateral misalignment. For simulating it in LabVIEW, we will be using the mathematical equation for the loss equation for lateral misalignment as shown in this angular misalignment losses using the relation and calculating the losses 10 log of eta angular. So we'll start with our lab view. The things that we require at the input is the core refractive index. Then we'll use a simple knob for lateral misalignment, micrometer. Then we need the refractive index of the medium. We need angular misalignment. Again, we'll be using a dial. In addition to this, we require either we can use delta or directly use a numerical aperture. So we will be taking numerical aperture. Now to see the output, we'll be using the dial lateral misalignment loss in dB and angular misalignment loss in dB. Now we want to see the graph of variation of lateral misalignment loss with lateral misalignment. For that, we'll be using our extended XY graph, and also same we'll be using for angular misalignment loss versus the misalignment in degrees. Now we have all our inputs on our front panel. We'll be making our block diagram. Now we will be using the formula board to calculate our lateral misalignment and angular misalignment losses. So for that, go to the mathematics, script and formula board. Now in this, we will be writing our formula for the lateral. We'll be using N1, N, NA, lateral misalignment, and also we need the third value is the core radius. So that we don't have it here, we'll just go to our front panel and have one more input terminal of core radius in micrometers. Now we'll simply write our formula. Now we have written our formula as per our manual and just press OK. And now we will make our connection from the input terminals to the formula board. Now the output that we have is the eta value. Now we need to convert it into loss by, now to calculate the loss, the value is minus 10 log of the value. For that we'll be going to elementary, exponential and log 10. So just feed it here, then multiply it with 10. To the other leg, we will create a constant and give it the value 10. So this gives us a value 10 log. We need to negate it. And this will give us our lateral loss. Now if you want to see the plot, lateral misalignment losses versus the lateral misalignment. So to the X, we will connect the lateral misalignment. Y, we will connect the losses. To the reset button, we will first create a constant and make it false. Now we are ready to observe it. Similarly, we will do the same thing for the angular misalignment by taking the formula board, selecting the inputs N1, N, theta, numerical aperture. We have written the formula as per our manual. Now we'll make the connections with the input terminals. Now again, to get the losses, we need to take 10 log of the value and negate it. So we'll go to mathematics, elementary, exponential, 10 log. We'll use a multiplier and we can simply directly here multiply it with minus 10. So either we could do 10 and negate it or minus 10. And create a constant for the reset and set it at false. So now we have everything set on our block diagram. Now we will see the observe the output. So we can just run it and see by we setting our appropriate values. We can again have our digital displays. Now after setting the values, we can clearly see we are getting the correct values of angular and lateral misalignment. I just want to add here that when we are putting this formula, the value of theta has to be in radians. So when we are putting theta, it is into pi by 180 because this theta input is in degree. So that needs to be taken care. Then only we'll get the correct result. Now what we see is we are not getting the plot. So for getting the plot, we want a continuous variation in the values. For that, we need to use a while loop. This will help us to continuously run the loop and get the values to this red button loop condition. Now to this loop condition, we will just say create a control. It will give us a stop button. Now once we have this, we can just again run it and see whether what we are getting. Now we will try to vary our, we can see to get a better visibility of the result. We also can change the line width and similarly for this. What observe is we are getting a straight line. The reason for it is that this amplitude, which is a loss which is in dB, has to be in the logarithmic scale. So what we will do is now we'll go to the property, change our x and y label and also change the y scale in logarithmic. So we'll go stop run and go to the properties. Our x, the name is align converter, and now we will set for the y dB and the scale we will keep it as logarithmic and press alignment in degrees, and for the y-axis it is angular misalignment loss in dB. Now we can set the scales so that we can see the results clearly. And for a fixed value of input values, we will vary the lateral misalignment, and we can see the plot we get. Now we will simply change the medium and again vary our lateral misalignment and see the impact of, as the medium becomes more and more matched, you can see that it is moving more towards the value of. Now for a particular set of values, we'll just vary the lateral misalignment and we can clearly see the plot is visible. Now the same we can get for a different set of value of refractive index, and is there between the medium and the fiber refractive index, the losses are increasing. Now same thing we'll do it for a particular set of value of numerical aperture. We'll just vary our angular misalignment and you can see the losses, and now we have it for a left. And same thing we can again do it for the same numerical aperture. We can vary the angular misalignment. So as the refractive index of the medium becomes more and more matched to the refractive index of the core, then the losses are reduced. So this is what you have to do in your practical, and prepare an observation table for a particular set of input values. What is the lateral misalignment losses for changes in the lateral misalignment when the refractive index medium of the medium is much higher than the refractive index of the core, and when it becomes matched. Same thing you need to do it for angular misalignment for the same numerical aperture and when the numerical aperture is changing. Thank you.